Okay, so welcome everyone to QUT's Centre for Data Science Under the Hood seminar. My name is Joshua Bond. I'm a postdoc at QUT. Just like to start by acknowledging that I'm here on Turrbal and Yagara country where QUT sits, and that's where I'm joining from today, and just pay my respects and acknowledgements to elders past and present. Today we have Dr. Leah South. Leah's a lecturer in statistics at QUT and an associate investigator for the Centre for Data Science and an associate investigator for ASEMS when that existed. And Leah's research interests are in Bayesian computational statistics, especially variance reduction techniques, scalable Monte Carlo, and approximate Bayesian computation. I think Leah's work is of a really high standard, and she was awarded an outstanding thesis award for her PhD, which is stellar. And I'm really excited, not just for that reason, but I'm really excited today to hear this talk from her. So feel free to write questions in the Q&A box as we go. Leah will get to them if she can, and there'll also be an opportunity to ask questions at the end of her talk. And with that, I'll hand over to Leah to get started. Thank you.
Cool. Thanks, Josh, for the introduction. So I'm going to be talking about improving Monte Carlo estimates with control variates. So the beginning part of the talk is going to be like a brief tutorial, I guess, on control variates. And then I'm going to go into some of the novel methods that I've worked on with these collaborators here. So that includes Chris Javandi from CDS. Okay, so the setting of this talk and the methods I'm going to be talking about are basically that we have a set of n samples from some distribution. I'm going to call that distribution pi. And we want to evaluate the mean of some function f with respect to pi. So you can write that. I like to use in this notation most of the time, or you can write that as an integral. So for example, maybe you want to estimate a mean or a variance or some other expectation like that. So typically, if you're in that setting, then you go, I guess, straight to the vanilla Monte Carlo estimator. So if your function, you've got this function of f of interest, you'd evaluate f for each of your samples and you just take the mean. Okay, so that's what I'm going to call the vanilla Monte Carlo estimator. And to get some intuition on how that works, if your samples were drawn independently and identically from pi, then this estimator here would be an unbiased estimator for our true quantity of interest. And the standard error is of the order 1 on root n. So if you wanted to reduce the variance by a factor of 100, you need to get 100 times as many samples. And often that's going to be expensive because your sampling might be through, say, MC or something like that. And each iteration is going to involve a likelihood computation. So whatever your sampling method is, it can be expensive to get samples. And so basically, we want to think about a way to improve on this without getting more samples. Okay, so this talk is going to describe several estimators to improve upon this. And the stuff that we need is we need our set of samples, and we also need some associated gradients of the log target. Okay, so we need our pi, our PDF for our distribution that we're sampling from to be, the log of that to be differentiable. Okay, so there's lots of different applications. Vanilla Monte Carlo, so that's, say you've got IID samples, you can have gotten your samples from MC, and if you've done that with a gradient-based sampler, then you have this extra information for free. You could have gotten the samples from sequential Monte Carlo. You can have even used a stochastic gradient method where you have unbiased estimates of this. So all of those are applications where you might want to use these types of methods. But some of the methods can also be used just more generally. You can have deterministically picked a grid of points and you can still use some of these methods. So they're pretty broadly applicable. And I wanted to mention also that all the methods that I'm going to talk about are in this R package CV that I produced. So I'm going to give a couple of examples in case you actually want to use this in your own work. Okay. And I've also got here an illustration of the kinds of improvements we can hope for. So this is, I think it's a one-dimensional ODE example in Bayesian inference, and we're trying to estimate the posterior mean. So we've got a gold standard in red, which was based on a really, really long MCMC run that took a long amount of time. And then these box plots are from 100 different runs with 10 samples. So I run MCMC for 10 iterations, which if you do MCMC, you'll know is not very much. And then in this case, I've just estimated the mean using vanilla Monte Carlo. I've done that 100 times and you can see it's got high variance. And then over here, I've used the exact same samples as what I did over here, except I've applied control variates. And so you can see that we have a very much reduced variance estimator. So in our one run with 10 MCMC samples, the variance is very small and so much smaller that it's actually better than using MCMC with 1,000 iterations. Okay, so that's kind of the motivating area. Now I'm going to go through some background. I'm also going to take my jumper off because it's getting hotter in this room now. Okay, so basically all the methods I'm going to talk about are control variates. And so here's the definition of control variates. Basically, what we had in black was the vanilla Monte Carlo estimator. And then to do control variates, we add the blue stuff. So you can see that rather than evaluating F at each of our samples, we're evaluating F minus F tilde. And then to keep the expectation the same, we need to actually add on the true expectation of F tilde. So this thing F tilde is a control variate, and you can also think of it as an approximation to F. So we want to get an F tilde or a control variate that gives us an approximation that's very close to F. But the difficult thing is that we actually need to be able to evaluate this. And the whole reason we're doing this is so that we can estimate the expectation of F. So, you know, getting the expectation of F tilde with respect to pi is also typically challenging, and that's the main challenge with control variates. So the intuition on why we actually do this, why do we actually replace F with F minus F tilde plus its expectation? The intuition is that if you've actually got IID samples from pi, then you've still got an unbiased estimator, but the variance of the estimator could be hugely reduced. So you could use, say, 10 samples instead of 1 million and get similar variance. Okay, the intuition on how that works is that the variance of the control variate estimator comes down to looking at this, the variance of F minus F tilde. This is just using basic first year statistics rules. And we can see that if we get the covariance between F and F tilde to be really high, or the correlation to be really high, then we actually can get the variance of this to be close to 0. Okay, so hopefully that gives some intuition on why we want to do this. And so here are the things that we actually need to be able to do it. Firstly, we need to be able to actually evaluate the true expectation of F tilde. We need to easily be able to compute F tilde at each of our samples. If F tilde is a very expensive function, then perhaps you may as well just get more samples rather than applying control variates. And then the final thing is we need reduced variance. Otherwise, there's no reason to actually do this. So we want the variance of F minus F tilde to be less than, hopefully much less than, the variance of F. Okay, if we don't pick our F tilde well, it actually could be worse. So you can end up with a worse estimator. But if we pick it well, it can be much better. Okay, so far I haven't actually described how we pick our control variate F tilde. And up until a few years ago, that was very application specific. So you needed to know a specific F tilde for your context that had a known expectation. And that's typically difficult, but it had been done before, for example, in option pricing. So if you're from finance, you might want to look into this reference here for your area. Okay. But as I said, that was up until a few years ago. Now there's an approach to get control variates that's much more broadly applicable. And it's based on something called Langevin-Stein operators. So I'm not going to go into heaps of detail about it, but I'll give enough that hopefully you know what the definition is. Okay, so the idea from Chris Oates and others' paper in 2017 is that you pick your approximating function or your control variate to be some constant plus a so-called Stein operator applied to a function. And this function G is something that we need to specify. So if we pick G well, we'll get huge variance reduction. If we pick G really poorly, we could get worse variance. The reason that this works is because this Stein operator has this nice property here. So the Stein operator applied to G has zero expectation under some pretty mild conditions on G and pi. So because of this, we know the true expectation of F tilde is just a constant. Okay. There are lots of different Stein operators, so lots of different ways to define this curly L, but typically we'll use the Langevin Stein operator. And one of the definitions for that is here. So you can see it involves some first order gradients of G. Now, as I said, we've defined G, so that can be as easy as we want it to be to evaluate. We've got some second order gradients of G. Again, that can be made very easy. And then we have the gradients of the log target. So that's something that I said at the beginning of the talk we need for these methods. And it's something that's already available if you've used a gradient-based sampler. Okay, so this is the definition. I mean, it doesn't look particularly pretty, but if you plug in a specific G, then you have a nice form for what your approximating function looks like. Okay, so we've given the general form. Now, is it easy to compute? Well, that depends on G, but I've kind of written out, I've plugged in this version of F tilde into the formula for control variates. We have that the true expectation is A, so we plug that in and we end up that this is the final control variate estimator. So the remaining thing to do is to actually pick our G well so that we get reduced variance. And the key is going to be to pick some G from a wider function class by optimizing some criterion. Okay, and that's basically what all the existing methods are based on. They're based on picking a different function class. So firstly, there's zero variance control variates. And that's based on picking this function G to be a polynomial. So basically, you plug in a polynomial and you get out that the approximating function looks like this. So it kind of looks like, keeping in mind we want F tilde to be as close to F as possible, it looks basically just like a linear regression problem. We've got an intercept, we've got some coefficients, and then we've got some covariates. And these covariates are a function of the samples and the gradients of the log target. So when people actually have gone to estimate the A and the beta, they've just done that using ordinary least squares. Okay, by the way, if there's anything that's not making sense, please feel free to let me know via the chat and I'll try and clarify before we keep going. Another way to pick G is to pick it from a Hilbert space. And there's a nice closed form solution for the estimator here. So basically, to actually perform this non-parametric version of control variates, we pick some kernel, for example, a Gaussian or Matern kernel, where we need to tune its parameters. And then we apply the Stein operator to the kernel, and we've got this closed form solution here. So it turns out this is an n by n linear system, and so it's pretty expensive to compute for large n, but it can go quite well. If you're someone who knows about Gaussian processes, then you might prefer this version of the explanation. So basically, we're putting a Gaussian process prior on our function f. And the Gaussian process prior has zero mean and a covariance that's based on this Stein operator applied to the kernel. Okay, so these were, I guess, the main two Stein-based control variates that are out there. So they're the two main broadly applicable control variates. And I just wanted to summarize their properties before I show you how to do this in R and then go through some new methods. Okay, so control functionals, its computational complexity is order n cubed. So if you have a lot of samples, it's going to be very expensive to compute. The zero variance control variates, which is a parametric approach, it's linear in the number of samples, but it's cubic in essentially the dimension and the polynomial order. Okay, in terms of actual performance, zero variance control variates, for reasons I'm not going to be able to go into in this talk, it can actually give you zero variance estimators for the specific setting listed here. And when I say zero variance estimator, I mean you can use, say, 10 samples, you can apply zero variance control variates, and it will give you the true expectation, not an estimate. So that's obviously a really nice property, but it's for pretty limited settings. Control functionals, it doesn't have that property, but it does have this nice convergence rate. So basically, as you get more and more samples, the performance is going to keep getting better. And it's actually a better convergence rate than vanilla Monte Carlo. The amount better depends on the smoothness of pi and of f, and also on the dimension, where obviously higher dimensions are going to go worse. Okay, and then both of these methods are based on all derivatives being available, so I'll address that as well. Okay, so I think at this point, it's worth taking a quick look at how to do this in R. And I'm not going to go too much into the code, but I just want to show you the general idea and hopefully convince you that it's relatively simple to apply. Okay, so I'm just going to switch to a different document. Okay, so in this document, I've got a simple linear regression model. It's about the strength of these radiator pine trees that you can see here. So it's a Bayesian inference problem. We're trying to estimate the posterior mean of the intercept, the coefficient, and the variance in a linear regression problem. So there's some priors on our things that I'm not going to talk about. And then also when we're doing our sampling, we do a log transform, but again, that's not super important. I guess the main thing is, sorry, I'll just scroll down a bit. I've got some code at the top to actually get the samples, but then to actually perform control variates, what we do is we get our samples. So that's what I'm doing here. This is basically a gradient-based MCMC algorithm, but you can replace that with whatever you want. I'm extracting the samples and the gradients of the log target. In this case, that's the gradients of the log likelihood plus the gradients of the log prior. So, you know, everything, oh, sorry. Not very good at using this, this viewer for PDFs, but anyway. Okay, so you can see I've got the samples, I've got the gradients of the log target, I'm estimating the posterior mean. So the integrand is just theta. And then since I've done a log transform in the last parameter, I'm just going to take that back to the original scale. So we've got samples, gradients, thing that we're trying to estimate the expectation of. So if you were doing vanilla Monte Carlo integration, you would just take the mean of f. Okay, so in R, that would be col means f. And this would be our estimate of the posterior mean for the intercept. This is our estimate of the posterior mean for the coefficient of x, and then, or the slope, and then this is the estimate of the posterior mean for sigma squared. Okay, if you instead wanted to do zero variance control variates, then I've got this function here. So the first thing is the integrand that we plug in, so f, then we've got our samples, we've got our gradients, and then you can specify different options. So in this case, we're using a second order polynomial, and this part here probably won't make much sense for now, but I'm saying don't apply regularization when estimating the coefficients, just use OLS. So you do that and you get a different estimate for each of our posterior means. And then control functionals is similar. You have integrand, samples, gradients, and then you need to pick the tuning parameter of the Gaussian kernel. And so I've given a few options to that, and it picks between those. Okay, so I guess, you know, you can see that you get different estimates, but it's kind of hard to tell which one's the best. That's, I guess, a general problem with control variates. There are some methods to help you pick, which I can talk about later. But because it's hard to convince you that these methods are better based just on some numbers, I thought I'd give some box plots. So basically, I've just done this 100 times to get 100 different estimates. And I've plotted the estimates of the posterior mean, in this case, for the intercept. Okay, so you can see that vanilla Monte Carlo has very high variance. Then if we do ZVCV, we get hugely reduced variance. And same with control functionals. These are a couple of new methods that I'll talk about later. Then for the slope, this is the estimates of the posterior mean from 100 runs again. You can see, again, huge variance reductions with ZVCV and control functionals. So the reason this is helpful is because we're using not many samples and it's actually getting huge variance reductions. So essentially what we can do is, rather than increasing the number of samples to say 1 million, we can still use the whatever 100 samples and then apply control variates and get similar performance. Okay, and then you can see again for posterior mean for sigma squared, we're getting big variance reductions. Okay, I can see a question. Yes, so David says, I thought the zero variance strategies would have zero variance. Can you explain? Yes, so they have zero variance only in one specific setting. It's when your pi, the thing that you're sampling from, is a Gaussian distribution and the function that you're trying to estimate is a polynomial. In this, so it's polynomial in theta. In this case, we have got polynomial f for the first two things because the integrand is just theta essentially, but it's not a Gaussian target. It's the posterior from our linear regression setting. Yeah. Okay. So now that takes me to the new part of the work. So we're going to talk about two papers. Semi-exact control functionals we had published in Biometrica, I think it was this year. And basically the idea is that we want to balance the potential exactness of ZV/CV with the improved convergence rates of control functionals. So we want to have exactness for Gaussian targets and polynomial functions, and we also want to have convergence rates that are better than vanilla Monte Carlo. And then the second thing is regularized ZV/CV. So essentially, we want to improve the flexibility of ZV/CV. We want to improve performance in high dimensions. And we also want to be able to do this when we only have some of the gradients. Okay, so semi-exact control functionals, as I said, it's balancing these two nice properties. And the idea basically was motivated from something in the numerical integration literature. So in numerical integration, they might replace the the expectation of f with an expectation of f tilde. And they do that based on either enforcing exactness on a set of pre-specified functions or finding a minimum norm interpolant. So there's these two kind of streams of numerical integration approaches. You might notice that this first one kind of sounds similar to ZV/CV, the parametric approach, and this one sounds similar to control functionals. Control functionals actually is an interpolating method. Okay, so there was a paper in 1949 in numerical integration literature that combines the two ideas. So it enforces exactness on some set of function, and it finds a minimum norm interpolant with the remaining degrees of freedom. The problem with Saad's method is that it isn't typically feasible for Bayesian inference. So if you're not a Bayesian, you should know that in Bayesian inference, our distribution that we're sampling from, we can't actually evaluate the PDF fully. We can only evaluate up to a normalizing constant. So the reason that it's difficult in Bayesian inference to use these methods is because we need to get expectations of certain functions with respect to our posterior distribution. And because we don't know that normalizing constant, that's difficult. So it turns out that if we apply a Stein operator, that the operator I mentioned earlier, we can solve some of these issues. So basically this new method, semi-exact control functionals, is doing that. Okay. So now the interpolant looks like this. Okay, so I mean, it doesn't look particularly appealing, but this first part here is very similar to ZV/CV. We've written it slightly differently. I've got phi instead of p, because technically you could use any parametric basis, but if you were using a polynomial, then this part here would be exactly what we have in ZV/CV. And then this part is very closely related to control functionals. So this is the Stein operator applied to a kernel. And so you'll notice that we're kind of combining both of those methods. Our f tilde is almost just the sum of the two previous f tildes, but the key is in how we pick our intercept and our coefficients, so our a's and our b's. Okay, so we pick those so that we have this exactness property, and it turns out that this gives us exactness for Gaussian targets and polynomial functions. And we also want to have this nice interpolation property. So I'm not going to go into too much detail about how to do that, but we can write this up as a linear system, and there's a closed form solution. Again, if you know about Gaussian processes, then you can think of this as using this Gaussian process prior for F. So basically, our Gaussian process covariance is the same as control functionals, but the prior mean is different. This is actually based on ZV/CV. So it's kind of like control functionals, but informed a bit through ZV/CV. Okay, the downside of this method is that it's actually pretty expensive because the linear system is kind of expensive to solve exactly. So we've got a couple of ways to speed that up. We can use a Nystrom approximation. And so basically the difference is that the new interpolating function looks like this, where our n0 is much smaller than our original sample size. So you can kind of think of this as a random projection method. Okay, and a couple of properties are that it's exact for qth order polynomials for Gaussian targets. Or if you want to be fancy, you can say that it's exact in the Bernstein-von Mises limit. So as the sample size, so in Bayesian inference, as the number of observations goes to infinity, our distribution typically goes to a Gaussian distribution. And so we've got this nice property here, and that's the same as ZV/CV. It was really hard to get convergence rates. So we don't have a theoretical proof that we've got a better convergence rate. We've done some empirical studies and it looks better, but we don't have the proof of the convergence rate. However, we do have a consistency result. So the estimator goes to the true thing in probability as the number of samples that we've got from pi goes to infinity. And the nice thing about this is that it's true even if you're actually doing bias sampling under some settings. So you could be doing an MCMC algorithm that's fast but biased. So it's not quite targeting pi, but it's targeting something close to pi. And so in that setting, you can actually have consistency. And so basically you can think of this as bias correcting because standard MCMC wouldn't have that property. Okay. I wanted to demonstrate that empirically. So on the left, I am using a MCMC method that is targeting pi. On the right, I'm using an MCMC method that's not targeting pi. So on the left, you can see that as I increase my sample size, the estimates kind of converge onto the true value, which is this black horizontal line. Whereas in the bias sampling approach, for most of the methods, so vanilla Monte Carlo integration and ZV/CV, so the orange and the green, as you increase your sample size, you're not converging on the true thing because it's a bias sampling method. However, if you apply control functionals or semi-exact control functionals, then you do converge onto the true thing. And also you actually got variance reduction as well. So it can go much better. So you can see that in either case you have variance reduction, but if you use control functionals or our new semi-exact control functionals method, we can also get bias correction. Okay, and now I'm just going to talk about a simulation study. Okay, so I guess you don't need to worry about this too much. You can pick different kernels for your, so for both control functionals and semi-exact control functionals, you need a kernel. And here I've just picked a rational quadratic kernel because that went well across the board. Okay, I needed some way to report efficiency because it's hard to do box plots when you want to show lots of things. So instead of doing box plots, I'm reporting statistical efficiency like this. So it's the ratio of estimated mean squared error between the vanilla estimator and the estimator in question. So if this was, say, 100, then it means our mean squared error is 100 times lower, and that's without getting any more samples. This one's actually overall efficiency, so computational isn't the best name. Basically, it's combining this and the computation time. So yeah, it's taken into account that, yeah, there's a bit of extra cost in performing the control variates, but hopefully it's still worth it because it's not as expensive as getting more samples. Okay, I'm going to give an 11-dimensional example, a 61-dimensional example, and a Gaussian example, which is good to illustrate different dimensions. So I've chosen not to go into heaps of detail about how these examples work, but I guess if you want that kind of information, it's in this document here. for one of the examples. Okay, so here's the Gaussian example. On the left, we've got statistical efficiency. On the right, we've got overall efficiency. The light blue line is vanilla Monte Carlo. Everything's relative to that, so it's always at 1. In green is zero variance control variates with a first order polynomial, and then when it's dashed, it's a second order polynomial. Dark blue is control functionals, and orange is semi-exact control functionals. I guess don't worry too much about the other ones for now. Okay, so what you can see is that for increasing sample size, the statistical efficiency is good for semi-exact control functionals. It's the best method. I guess it's not beating the other one. Sorry, this isn't a Gaussian example. This is a capture-recapture. I got confused. But you can see that it's the best method, not by a huge amount, but it's going similarly to the other best performing method, which in this case is control functionals. Same with computational efficiency. It's a pretty similar story. Okay, in the logistic regression example, again, semi-exact control functionals is going quite well in terms of statistical efficiency, not so well in terms of overall efficiency because this is a very cheap example. So we get better improvements the cheaper, the more expensive it is to sample from pi. Okay, so I mean, these two aren't that convincing, but the important part is that control functionals is the one that was going well here before, and ZVCV is the one that was going well here before. So basically we found that regardless of whether it was the parametric or the non-parametric approach that was going well before, our method can go similarly or better given enough samples. And then here's the Gaussian example. So in this case, we've got increasing sample size and increasing dimension. Both of these are statistical efficiency because it's extremely cheap to sample from a Gaussian distribution. So really in practice, you wouldn't apply control variates. Okay. And the other thing I should mention is that it's a Gaussian distribution, but none of the methods are exact because the function here isn't a polynomial. Okay, so you can see that for higher sample sizes, semi-exact control functionals outperforms everything else. And the numbers here are about, I think that's 300. So the mean squared error is about 300 times better than vanilla Monte Carlo. And then the performance deteriorates for higher dimensions, but it's still the best performing method. Okay, and then the last thing is, I just wanted to show basically that I picked a rational quadratic kernel and I tuned the parameters really well, but what would happen if I hadn't picked the kernel so well? And so you can see control functionals depends a lot on the kernel choice and the way we picked our parameters. So I've got Gaussian return rational quadratic kernel and then cross-validation or a heuristic. So the performance of control functionals depends a lot on that. Semi-exact control functionals, we don't have to be quite so careful in how we pick our kernel. And then the last thing I wanted to say about that method is that we have an approximate upper bound on the quality of our approximation basically. So this I is the true expectation or integral, and this is our estimate of it. And so this is an upper bound. We can't evaluate exactly, but we can approximate it. And you can see that the approximation is going reasonably well at upper bound in the mean absolute error. Okay, now I just thought I'd briefly show you how to do this in R. So it's basically one line. Okay, this is the one line. So semi-exact control functionals, cross-validation to pick their tuning parameters. So again, integrand, samples, gradients. We need to pick a polynomial order for the parametric part, and then we need to pick a bandwidth for our kernel essentially. So this is just giving it some options. And in this case, you can see it's going quite similarly to control functionals. Okay. If there's any questions, by the way, please do let me know on the chat. Because now I'm going to move on to the last method, which is regularized zero-variance control variates. So the motivation for this is that ZVCV, in the literature, people had previously only used first or second order polynomials for their control variates. So can we get improved performance by using higher order polynomials? And then can we use regularization to improve performance? The nice thing about regularization is that we can actually do this without introducing bias. So there's a couple of conditions on that, but typically if you're using regularization like Lasso or ridge regression, you are going to get biased estimates of the coefficients. So you're going to introduce bias into your inference. But in this setting of doing it via control variates, we don't necessarily have to introduce any bias. Okay, so just to convince you that it was a good idea to consider higher order polynomials, here's a one-dimensional example. You can see that the darker colors are the higher order polynomials and the black one is automatically picking the polynomial order. So if we've got enough samples, the higher order polynomials go well. And you can see in this case, the efficiency is about, what's that, 10 to the 18 maybe at the best point. So that means that the mean squared error is 10 to the 18 times lower than what it was in vanilla Monte Carlo. And this is actually for an ODE example. So it's not like it's a super simple distribution. Okay. So we want to increase polynomial order, but obviously there's a limit to which we can do that because the higher order polynomial we have, the more coefficients we need to estimate. So we're going to be using more degrees of freedom and we might get overfitting, or perhaps it's not even going to be possible to estimate the coefficients. So we can't use OLS or ordinary least squares. We instead want to use some kind of penalized method. So we've looked at ridge regression and Lasso, and then also this other method that I'll speak about in a minute. Okay, so ridge regression, here's how we're estimating coefficients. So this part in black is almost identical to how we did things in standard CVCV. The only difference is this S to say that I've standardized these terms. Okay, the difference is that we're adding lambda times a squared L2 penalty on the betas. So yeah, it's basically just an application of ridge regression. And this can be interpreted as a computationally efficient version of control functionals. So even though it's a ZVCV method, you can think of it as control functionals with this kernel here. Okay, and then if you're familiar with penalized regression methods, you'll know that Lasso can often outperform ridge regression. And so here is the Lasso alternative. So it's just adding on lambda times an L1 norm penalty on beta. Okay, so those were two ways to reduce the number of coefficients we need to, well, to improve the problem for a lot of coefficients. Another way is to just kind of think a bit more about your context before you apply the control variates. So maybe if you're estimating the posterior mean of θ2, and you know that θ2 is close to independent of the other variables, you don't really need your polynomial to depend on all of the dimensions. Maybe you can just make your polynomial a function of θ2. So basically, you pick a subset of the variables that you think are going to be useful for your context, and then you restrict your G to be only a function of those variables. So basically, we're picking our subset based on prior knowledge about whether these two terms are going to be helpful in predicting the mean of f of theta. Okay, so most of the time you will lose the capacity for huge variance seduction if you have a lot of samples, but you'll get better performance if you haven't got many samples. There's only one context where you can't lose any information by doing this, and that's if your function is truly only a function of the subset. Now this one's actually super common. If you're estimating a marginal posterior mean, then that will be the case. And then the other requirement is that the subset that you're picking is independent of the rest of the variables according to pi. This one's obviously a lot less common, but hopefully this gives you some intuition on when this might be a useful method. Okay, now I've presented a whole bunch of methods. We've got ZVCV where you have to pick the polynomial order, so first, second, third, etc. You could pick to use ordinary least squares or Lasso or ridge regression, or you could pick things in advance. And so in practice, we only want to apply one of these methods. So we also introduced a way to pick between the methods, basically. So the idea is to use cross-validation based on the average sums of square residuals in a holdout set. So basically, for each combination of penalization type and subset, we're going to start with a first-order polynomial and keep increasing the polynomial order until the average cross-validation error gets worse. And then just pick the overall method that has the lowest error. Okay, so that's one way to get over the problem of picking between different control variates. It's not perfect, but often it performs pretty well. Okay, so now I just want to do a simulation study to convince you this is useful. In the paper, we do SMC to get our samples, and we have a couple of extra details around that, but I'm not going to give you those details here. Okay, so we've got a 1-dimensional example, an 11-dimensional, and 256-dimensional. Mean squared error, efficiency is defined in the same way. And okay, here's some results. So the 1-dimensional example was really just to convince you that higher order polynomials were good. And in this case, that the cross-validation method worked well. So I've already shown you this picture earlier. This is just saying that the more samples you have, the higher order polynomial it picks. And that kind of makes sense because higher order polynomials are more flexible. And then control functionals is actually quite poor relative to the other methods here. That's control functionals in red. Okay, then we've got a capture-recapture example. So you can see that in black is the cross-validation method. It's going quite well. The different blues are different ZV/CV with higher order polynomials for the darker colors. And the dashed line is Lasso. I think just ignore the dotted line for Ridge because honestly, Ridge didn't go that well. We only presented it in the paper because it had that nice relationship with control functionals. Okay, so what you can see is that you can, so this blue here, that is a 3rd order polynomial. And you can see that we can actually start applying that sooner if we use the Lasso method. Okay, so I'm not too excited about these results, but I would like to show you also some results for a different expectation, basically, and then also for a higher dimensional example. Okay, so these are 2 plots for the same example, but we're doing evidence estimation here. So basically, we've got a different integrand or different function f. So you can see now cross-validation is the best performing method, and the higher order polynomial with Lasso are also performing very well. And then again, in this different estimator of the evidence, we've got a similar story. Control functionals is going okay, but it's got pretty high variance, whereas our approaches are going pretty consistently well. And then finally, here's an example that's very high dimensional. So, I mean, if you're in certain areas, you might think 256, that's really not high dimensional. When it comes to control variates, it is. People typically only look at dimensions of less than or equal to 4. So 256 is actually very high for control variates. So we've got vanilla Monte Carlo integration. Its efficiency is 1 because everything's relative to that. Control functionals is twice as good, both in terms of statistical efficiency and overall efficiency. But we can't actually apply any of the previous ZV/CV methods because we don't have enough samples. I think we've got 100 samples here and we've got 256 dimensions. So we can't do a first order polynomial. That would require 257 parameters to be estimated. Okay, so we can't do ZV/CV, but we can do it if we apply the new Lasso and Ridge regression methods. And you can see that it's 21 times better than vanilla Monte Carlo integration. Okay, and then basically these methods here are looking at, if you're estimating the marginal posterior mean for say theta 123, then you won't include theta 1 to theta 122 and so on in your polynomial. You're only going to include the one variable in the subset. Okay, So here we get even better statistical efficiency. We've got up to 50 times better, both in terms of statistical efficiency and overall efficiency. And then cross-validation also performs quite well. So that was the new method for picking between approaches. Okay, this is also pretty simple to implement. So I'll just take you to that code. Basically, again, integrand samples, gradients, and then we feed it some options, in this case, a third order polynomial, and by default, it will apply regularization. Okay, so that's all the new methods. I'll just quickly do a summary. Sorry, this has gone a bit longer than I thought. But the summary is that we have a set of n samples from pi and associated gradients of the log target, and we want to evaluate an expectation of f with respect to pi. So this talk proposed several new methods which improve upon this vanilla Monte Carlo estimate, and all of the methods use control variates. The two novel methods I presented were semi-exact control functionals, which is in Biometrica. It combines the exactness of ZVCV with the improved convergence of control functionals. And then there was regularized ZVCV, which has improved performance in higher dimensions. It lets us possibly use a subset of derivatives. Oh, I didn't explain that. Basically, if you use a subset of the variables, you only need those gradients of the log target. You don't need the rest. And it also has automatic control variate selection. There's a brief table here summarizing theoretical properties. So I've got a review paper that includes this in there. The method is available on CRAN in the package ZVCV. And then a couple of limitations in future work. So we need to limit the polynomial order in practice, because if you try and pick a polynomial order of say 100, when you've got 100 dimensions, that's going to blow up and be a crazy number of coefficients to estimate. So computationally, you can't do that. Cross-validation is a computationally expensive way to pick the method. And then I guess the most relevant two here are we want a gradient-free alternative. So you don't actually have to get gradients of the log target. That would help to apply in say ABC or in really expensive ODE models where getting the gradients might be too prohibitive. And then finally, the performance is going to depend on how you actually parameterize theta. If you do your sampling on the log scale, then often that's going to go better than if you do your sampling not on the log scale. But the parameterization will affect things. Okay, so that's it. I've got links to each of the papers, and I didn't talk about this one too much, but there's a review paper that talks all about this stuff and also other post-processing methods. Okay, thank you.
Thank you so much, Leah. If you could all join in me in showing some virtual appreciation for the wonderful talk she just gave. And if there are any questions, please put them in the chat or the Q&A now would be good, and we can see if have any questions. I've got one, Leah, maybe to get us rolling.
Yep.
I was just wondering, you made kind of a quick comment about the consistency property of even like a biased MC sampler that wasn't targeting the true posterior, and how control variates could correct for that bias. Is that something you'd recommend doing in practice? Have you seen people doing it?
Yeah, if you're using a biased, if you're using standard MC where you actually got a pi invariant Markov chain, then you don't really need a bias correcting thing because that is consistent. But if you've got a bias sampling method, then yeah, definitely. I've seen people using it, and I've seen that it can have quite good performance.
Yeah, that's pretty cool. Do you think that it's going to replace using unbiased, or not unbiased, replace using MCMC that's not consistent?
Maybe. It's hard to say, because I mean, it's hard to get theoretical comparisons of how this would go compared to using unbiased MCMC. But I guess it partly depends on how long you've got. If you really need to get your results quickly and speed is an important factor to you, then yeah, biased sampling and then applying these methods is typically way quicker.
Yeah,
especially if it's a really expensive likelihood. then applying, like maybe you can't get that many samples, and then applying these methods is like really cheap.
Okay, yeah, that's good to know that it's even more of a benefit for expensive likelihoods.
Yeah, expensive likelihood or expensive F. If it's expensive to evaluate your actual function of interest, yeah, it's also helpful there.
Cool. I also had another question, seeing as no one's entered anything into the Q&A yet. In, I think, one of the final tables, you had a look at, you were writing down, I think, the relative like computational cost.
Yeah, sorry, I probably should have removed that column. Basically, it was computation time for the method divided by computational time for vanilla Monte Carlo. So basically just the computation time to get your samples divided by the computation time for the question, for the method in question. So you can see that all of these, basically the cost relative to getting the samples is extremely low.
Okay, so like what a number close to 1 is saying is that the cost of getting the samples is just like orders of magnitude more expensive than doing the control variate method.
Yeah.
Okay, all right, yeah. So yeah, so large that you can't really even see it show up. It's more of like a blip.
Yeah.
Okay, yeah, that's a good clarification. There's a question maybe from David.
Sure, okay.
I'm happy to read it out if you'd like me to.
That's okay. So I read the first part of it. So my understanding is that the control variate strategy relies on us knowing the functional form of the distribution we're seeking to sample from. Yeah, it does at the moment. It requires that we know the PDF of the thing we're sampling from up to a normalizing constant. Or, I mean, the gradients of the log PDF, but typically that's even more difficult to know. Can you talk more about dealing with distributions that have very flexible functional forms? Sorry, I'm not quite sure I understand. Is that like distributions where you can't write down pi, or? Okay, for the second part about what happens, so sorry, can I just check? Is that about the function that we're trying to get the expectation of, or pi? Because if the function we're trying to get, okay. Yeah, I'm not entirely sure I understand, but we're not trying to approximate pi exactly. We're trying to approximate the relationship between our function f and our samples. And so if that's really wiggly or weird, then Gaussian process type methods like control functionals and semi-exact control functionals might go okay, but the polynomial method, ZBCV, won't. And if our approximation function f tilde, if that's really bad, we can actually end up with worse variance. So we can actually be doing something detrimental to our sampling. But you could potentially get an idea of that by doing some cross-validation.
Leah, do you
Thanks
know
for
of
the questions.
Leah, do you know of any methods that are working towards like not using the logs, the gradient of the log densities, or like maybe on discrete spaces and things like that?
Yeah, so Chris Oates and I were looking at trying to do gradient-free alternatives to this. Basically, it amounts to, like, in that case, it does actually amount to finding an approximation to Q and then correcting for that. But
sorry,
it doesn't.
What's Q in this case?
Sorry, pi. It does amount to finding an approximation to pi. And so, yeah, if you pick that poorly, it's going to go poorly. We haven't done heaps of investigation there, but I don't think it's going to work particularly well for discrete state spaces. And that's because the approximation needs to be continuous.
Okay.
But you can actually use different control variates based on different Stein operators if you've got a discrete state space. I'm not so familiar with that area though.
Okay. Yeah, so thanks so much for giving the Data Science Under the Hood seminar, Leah. It's been really interesting to see all this work and hear control variates explained really easily for me to understand. I think maybe we'll just send some more virtual appreciation for Leah giving the talk, and hope to see you all in the next seminar.
Oh, thank you.